In this series, I will describe an interpretation of physics where the universe is both local and real. This means that everything must have real properties at all times, and that interactions must occur through some direct physical means. However, not only is the scientific consensus that the universe is non-local, it's also commonly believed that all local theories have been ruled out through experimentation. As a result, they are usually dismissed out of hand and given very little consideration. Because of this, I will spend this video defending the idea of locality. I will argue that local theories are still plausible and haven't been entirely ruled out yet. This will be done by going over Bell's inequality theorem and any related experiment, as these are the most commonly cited evidence given to prove that the universe is non-local. There are other experiments which deal with locality, like the double-slit experiment and the Mach-Zehnder interferometer, but I'll have to get back to them in a later video, as the possible explanation I have in mind will require covering a number of other topics first. So Bell's inequality theorem isn't the only evidence for a non-local universe, but it is one of the most well-known, and in just the last few years, a Nobel Prize was given to several physicists for their contributions on these experiments. They therefore hold some importance in this debate, so I feel justified in starting this discussion here. Because the thing is, none of these experiments have actually ruled out locality. At least, not entirely. They only ever really test for a certain kind of local theory and can therefore only comment on those. Any local hypothesis outside of this framework has not been falsified and may still be plausible. This is actually a well-known criticism of these experiments. It simply involves the assumption of statistical independence in the local hypothesis. The local and real interpretation I will describe does not have this limitation, and as such, isn't actually addressed by any Bell experiment. As a result, it hasn't been ruled out by them. But it's not just that this interpretation isn't ruled out. It's possible that this kind of local hypothesis would match experimental results, or would violate Bell's inequality, which would mean that these experiments can actually be used as evidence in support of a local and real universe, like the alternative interpretation of this series. Describing the universe as local just means that all interactions must occur through some direct mechanism. When a cat knocks something off a table, that thing was moved by the cat physically touching and pushing it with their paw. There was a direct cause and effect mediated by some physical force. This may be obvious for most things in life, but can be harder to see at the extremes of nature. Like, it may appear as if the gravitational force between the Earth and the Sun occurs through nothing and by nothing, a sort of non-local interaction through the emptiness of space. Except the gravitational force is actually being mediated by the curvature of spacetime, which provides a direct physical mechanism through which to propagate. The gravitational force is therefore local. A consequence of being mediated through direct physical causes is that local interactions are restricted by the laws of physics, meaning interactions between two things can't happen faster than the speed of causality. This includes the gravitational interaction, which spreads out at this speed and no faster. As for the real part of local and real, that just means that everything has definitive properties at all times. This remains true even if we are unaware of what they are. So a real universe is one where the particles would have definitive properties at all times. While the largest scales of the universe are undoubtedly local in nature, the scientific consensus says that the quantum scale is non-local and probabilistic. Non-local means that quantum interactions can occur across any distance without a direct physical mechanism involved. An event on one particle can affect another particle across any distance instantly, even if this interaction would ordinarily need to occur faster than the speed of causality. The universe being probabilistic does not mean that particles aren't real. It just means that their properties are not in a defined state until they are measured. Since particles don't have definitive properties, they are described as existing in a probability space of all possible states, what is called a superposition. Non-local interactions are generally caused by quantum entanglement, where two or more particles have strong correlations between their properties where measuring one will change the properties of the other. The usual way to explain entanglement of properties is to start with something larger in scale, like a pair of gloves. They normally come in pairs, such that there's a left one and a right one, meaning the properties of left and right between these gloves is strongly correlated. If you randomly put each glove into separate boxes, and sent each box randomly to one of two separate people who are very far from each other, then when one of those boxes is opened by one person, they will not only know which glove they have, they will also instantly know what glove the other person has, because that property is directly related between the pair. But that is only because the gloves have real properties, which are correlated to each other. Quantum entanglement works somewhat differently, at least according to the standard model. When two particles are entangled, their properties become correlated, but what property each particle has is undefined until it's measured. So instead of having a definitive state, like up or down, they are in a superposition of being in all possible states. But what state they eventually have is correlated with their entangled partner. So in this case, if you send two entangled particles far away from each other in opposite directions, each to separate detectors, they do so without having a definitive state. It's only when one of the particles is measured that at that moment it takes on some state, like up. But, because it's part of an entangled pair, the measurement on that one particle causes an instantaneous interaction where the entangled partner takes on its definitive state, in this case down, even before it gets measured. And this interaction happens instantly, no matter how far apart they are, even if that means it would require faster-than-light communication. Or at least that's more or less the conventional interpretation of what's going on. The debate over locality goes back a century and comes down to how physicists should interpret certain quantum phenomenon, like the wave function collapse. While historically most physicists have sided with this non-local interpretation, there have been small groups of academics who advocated for locality. This includes Albert Einstein, who said that while he felt that quantum mechanics was good at describing the universe, it was nevertheless incomplete because it could lead to interpretations that are non-local, or what he deemed spooky action at a distance, because they could occur faster than the speed of causality. So Einstein and a few of his colleagues came up with a thought experiment to explain his position. Unfortunately, it was impossible to carry out, so it didn't actually end the debate. But in the 1960s, the physicist John Bell came up with his own experimental design that could be carried out. Over the ensuing decades, a large number of this kind of experiment have been done, and they all agree with the conclusion that the universe must be non-local in nature. Or at least, that's what they allegedly do, because they really only address one kind of local model. To understand this experiment, it's best to first talk about the property of spin, which is a measurable property of charged particles like protons and electrons that functions like angular momentum. Except, physicists don't think that this property is actually angular momentum, because for this to be the case would require that particles are physically spinning. And in order to produce this property, an electron would need to be rotating at least 1,000,000 times faster than the speed of light, which shouldn't be possible. So spin is just taken to be an intrinsic property that particles have. One way to measure spin is to use a Stern-Gerlach machine. Basically, these devices consist of two magnets of different strength that are separated by some distance, which creates a gradient in the magnetic field between them. When charged particles are shot through a vertically oriented Stern-Gerlach machine, they interact with the magnetic field and are then sent to a detection plate to measure their position. When this kind of experiment is run, particles always appear clustered together either on the upper or lower side of the detection plate in about an even 50-50 distribution, which is unlike what would be expected using just classical mechanics, where the prediction would be for such objects to be measured with an even distribution over the entire plate. The properties of spin up and spin down would come from the particle either being detected in the upper cluster or bottom cluster on the detection plate when measured. These machines can be tilted to any angle, which results in the particle being measured in an equal 50-50 distribution of up and down with regard to this new angle. And it's even possible to place these devices in a sequence so that each particle travels through multiple devices before detection. For instance, you can have one device positioned vertically, but set it up so that one of these paths is blocked, such as spin down. This way, only particles with spin up are allowed to pass through to a second device that is tilted 90 degrees to the first, or set horizontally. When this experiment is done, the particles that exit the second device will still be detected in an equal distribution to the right and left side of the detection plate. While this can be called left and right spin, this will usually still be designated as spin up and spin down in reference to the orientation of the device and magnetic field being used. So only spin up particles leave the first device, but the particles still evenly split into both up and down particles when leaving the second device. This can be further expanded to an experiment with 3 devices, where one of the paths out of the second device is blocked, such as for the down particle again. The third device would be oriented vertically, the same as the first. When this experiment is done, the particles that make it through to the third device will still be detected in an even 50-50 distribution for up and down spins once again. Even though only spin-up particles made it out of the first and second device, the particles that exit the third will still be measured as both up and down. The process that causes this isn't entirely understood, but there's definitely some interaction happening between the magnetic fields in these experiments and the particles moving through them. From experimentation, it was determined that a particle's orientation relative to an angle of a detector affects the chance that it will be measured with spin up or down. This probability can be figured out using square the cosine of half the angle between the particle and detector. For example, a particle that has been given a spin-up state with a vertical orientation that is being detected at a 45-degree angle will, according to this equation, have a slightly more than 85% chance of being detected as up. When the detector is at 90 degrees to the particle, then it has a 50% chance of being detected as either up or down. So spin is a property that particles have, and there is some interaction between these devices and the particles themselves. The original Bell's inequality theorem uses the property of spin to propose a way to experimentally test locality. The experiment uses 2 entangled charged particles that are created in such a way that they will have opposite spins to one another. They will then be separated by enough distance and tested in such a way that any interaction between them would require faster-than-light communication, which would be a sign of non-local behavior. Except that the measurement is taken at one of 3 angles, usually 120 degrees apart from each other. I will represent it like this, but this is not how the detectors look or work. The arrows just represent in which direction a particle would be measured as up if that angle were chosen. Each particle is only measured at one of these angles, and the selection of this angle is randomly made for each particle at each detector independent of the entangled partner. And this selection is made just fractions of a second before measurement, so that neither the researchers nor the particles could know what has been selected until right before the test is carried out. Or at least this time frame is so small that it would require faster-than-light communication between the 2 particles. After measurements are made on a large enough sample of entangled particles, the correlations between measured spin states are tested against the predictions of Bell's inequality to see if the measurement fits with either a local or non-local model. Of particular interest is how often entangled particles are measured with opposite spins. Under Bell's inequality, a local theory would predict that at the moment of entanglement, the 2 particles gain a permanent state for each of the 3 detection angles. This is how the idea of real properties is interpreted. And because of the way they are entangled, they will always have opposite spins. So the superposition of these local particles could look like one having spin up for all 3 angles, while the entangled partner has all spin down. Or it could be that one particle has something like spin up for angle 1, spin up for angle 2, and spin down for angle 3, while the entangled partner has spin down for 1, down for 2, and up for 3. All other permutations are mathematically equivalent to one of these 2 arrangements, so they're all we need to consider. If we work out what we would expect if this were true, then in the first arrangement the particles should measure opposite spins 100% of the time, because no matter which angle is chosen, they will always be measured with opposite spins. For the second arrangement, working out all the possibilities, we get a list of 9 different outcomes, depending on which combination of angles are chosen. Of these, 5 out of the 9 possibilities are measurements where the particles have opposite spins to each other, which is about 55% of the time. Since either of these 2 arrangements is possible for each entangled pair, the prediction for this model is for opposite spins to be measured between 55 to 100% of the time. But for a non-local theory, it says that the particles approach the detectors in a superposition of all possible outcomes. When one particle is measured, its wave function collapses and it gets a definitive state, such as being measured as up in the vertical axis. At the exact same time, the other entangled particle immediately has its wave function collapse, and it gets its definitive properties. In this case, as spin down state in the vertical axis. So if the vertical detector is chosen, then the particle now has a 100% chance of being measured as spin down. The other two detectors would be positioned 60 degrees away from the angle of this particle. So, if either of these two are chosen, then the particle would have a 75% chance of being spin up, which we can get from square the cosine of half the angle. Since each detector has an equal 1/3 chance of being selected, then working out the math, the entangled partner has a 50% chance of being measured with an opposite spin to its partner. It's the same no matter which angle we look at. So for a non-local theory, we should expect a measurement of opposite spins 50% of the time. When these experiments are carried out, they always result in measuring opposite spin states between entangled pairs 50% of the time. The non-local theory would seem to be supported, while the local theory appears to be falsified. So how can a local physical interpretation explain this? Well, it comes down to the assumptions being made for a local theory. As I said before, Bell's inequality only invalidates some local theories, those that follow from the assumptions made in the experiment. This is largely about what it means for a local particle to have definitive real properties and what a measurement is. Bell's inequality makes assumptions about what the answers are to both and then calculates probabilities based on this. What this comes down to is that Bell's inequality assumes that a local theory must have statistical independence, which means that the probability for one outcome doesn't affect the probability of some other outcome from happening. In this case, it means that the measurement of spin for a particle is not affected by the way it's measured. For a local theory in Bell's inequality, at the moment of entanglement, the two particles gain definitive spin states which are opposite to each other. These states are with regard to the measuring device, but they are determined instantly at entanglement and far away from the device itself. When the particles are measured, they don't interact with the apparatus at all. Instead, the detectors are merely revealing the properties that the particles intrinsically have for that measurement type. So there's no interaction that needs to be included in the expected outcome. Instead, simple probabilities are used. This contrasts with the non-local theory, where after one of the particles has been measured and it collapses the wave function, its entangled partner will have a definitive state with which to interact with the measuring device. The difference in angle between the polarization of the particle and alignment of the detector needs to be accounted for. Some kind of interaction occurs. The probabilities for this theory then are calculated with the way that the particle interacts with the devices locally and directly. And this behavior needs to be accounted for in the non-local theory because this interaction is just a part of quantum mechanics. It's an observed behavior of particles that some kind of interaction happens between particles and measuring device. It's simply not possible to make a measurement on a particle without interacting with it in some way that affects its behavior. However, this was removed from being considered a part of a local theory, despite this just being a fact of quantum mechanics, which comes from physicists believing that local and real particles would exist as inert spheres. And this is due in part to how the properties of particles shouldn't come from the physical act of spinning, because it would require faster than light travel. So all predictions for locality in science are done by modeling inert spheres. When I said that the prediction of classical mechanics for the Stern-Gerlach experiment was for an even distribution over the detection plate, this was based around modeling the behavior of inert spherical objects. Under this perspective, giving local particles statistical independence can be seen as throwing a bone in its favor, because at least in this way, these inert spheres have some property of up and down, even if this means they can't interact with any part of reality with these properties. However, under the interpretation that I will describe in this series, particles wouldn't be inert spheres. They would instead be dynamic interacting systems that are potentially made of smaller components. I will defend this position in future videos, but if particles do have some internal moving systems, then they should have intrinsic properties with which they should be able to use to interact with the world around them. And when we try to model their expected behavior, it should match the outcomes of these experiments, because it retains the fact that particles must be interacted with to achieve a measurement. So here's what I'd like to propose. What if particles just have definitive properties at all times that they use to interact with the measuring device? That is, particles have some property called spin that is very much like angular momentum. in that it's a resistance to motion. So when a particle is acted upon by an outside force, like a charged particle going through a magnetic field, the spin state interacts with this force and the environment it's in. Assuming this to be true, then just like angular momentum, this property of spin should be in some direction. And also like angular momentum, the direction of this force would most likely rotate with a precession. So it isn't really in any one absolute direction. At most, it just has an average angle that it points towards. And as experiments have shown, this spin state can either be manipulated to change, or can just change on its own over time. A particle can therefore have many spin states over its lifetime, but only one at a time. What we measure then is the result of an interaction between the spin state of the particle and the detector being used. That's all the changes that I will make in this assumption for a local and real particle, basically just making them actually local and real. So in this experiment, each particle can be created with a spin oriented at any angle, but the entangled pair will always have opposite spins to one another. With these spin states, they travel to the detector, which they interact with, which results in the measurement we see. There's probably some formula that could be found that will give the expected results faster, but I figured why bother when a spreadsheet can do these calculations pretty quickly. We just need to calculate how particles at any angle would interact with each detector, and then use this to find out the probability for detecting opposite spin states for each possible outcome. From that, it can be shown that there's a consistent 50% chance for measuring opposite spins from particles under these assumptions. No matter what combination of angles are chosen for two entangled particles, the probability for measuring opposite spins is 50%, which is consistent with experimental results, meaning this kind of local theory is not ruled out by Bell's inequality experiment. Although the fact that this works so well probably has something to do with the symmetry of this experimental design. Let's look at its arrangement through this representation. Because if we really think about it, we only need to consider the possibilities found between these two opposite 30-degree segments. The two entangled particles will be polarized with opposite spin states. So at most we only need to analyze half of the possible angles, because after 180 degrees, the particles have just exchanged spin states. Now if we keep rotating this experimental design by 120 degrees, we can see that it is made up of 3 repeated segments, this being the 60 degrees around both poles of each detector. So the probabilities that exist around each detector are the same. And so, all the possible outcomes can be found in one of these 60-degree areas on either side of a detector. But again, we only need half of this data, so we only need one 30-degree segment on either side of a detector. And within this region, there's always a 50% chance of measuring opposite spin states. Okay, that was a long-winded way to end up back at the same answer, but it leads into a problem that only exists for a truly local and real theory, that the spin of a particle can be oriented in any direction in 3-dimensional space. This time, rather than prove this with another spreadsheet, I figured why not just argue this logically, because the same issue with symmetry exists in this design with 3 dimensions. So once again, we need to only consider these two 30-degree segments. If we can also assume that there's no change in measurement when a particle is oriented towards or away from the device, then we can just look at half of the circle in the z-axis. So now we're only looking at 1/12 of the circle. We already know that when the particles are oriented vertically, they have a 50% probability for opposite spins. At the most extreme point on the z-axis, when both particles are 90 degrees to all detectors, they have an absolute 50% chance of being detected with opposite spins. And so moving on the z-axis means going from an overall probability of 50% of opposite spins to an absolute 50% probability of measuring opposite spins. And any angle in between these extremes results in an equal move in probability away from or towards the 3 measuring angles. So we should still expect opposite spin states being measured between entangled particles 50% of the time, which is consistent with experimental results, meaning that a local theory of the universe isn't ruled out by Bell's inequality theorem. And all that was required to make this happen was to include quantum behavior for quantum objects, because it's known that there is some kind of interaction between measuring device and particle. It's why this behavior is taken into account in the non-local theory. This is just a feature of quantum mechanics. This is why local and real theories haven't been ruled out, because it's only this narrow kind of locality that is covered by Bell's inequality theorem, where particles have properties but do not interact with the world around them. What I've gone over was the original Bell's inequality experiment, which used charged particles like protons and electrons. However, almost every real test of locality uses photons. While they are preferable for doing these experiments, they also make the experimental design much more complicated. On top of this complexity comes a number of different kinds of experimental designs, each of which can have its own inequality for analyzing correlations in the data. Starting the discussion with these experiments is a bit more time-consuming. Fortunately, by covering the original Bell's inequality theorem, the explanation for these other experiments gets much easier because they share the same problem. That a local theory must mean that there's no relationship between measurement outcome and the way that something is measured. That local and real means that the particles are abstract mathematical objects without physical presence in the universe. Which is the opposite of what this should really mean, that particles have real properties which they use to directly interact with the environment around them. Now, before getting into the experiments themselves, let's go over photons and the properties they possess. Photons don't have a spin state like electrons or protons. Instead, they are polarized along an axis. This is because photons propagate as electromagnetic waves. So instead of being spin up or spin down, a photon would just be vertically or horizontally polarized. It's also possible for photons to be circularly polarized, where the electric and magnetic field of a photon are out of step with each other. Devices like the Stern-Gerlach machine don't work with photons. Instead, polarized filters of some sort are used to explore their properties. These filters have some alignment that only allow photons with similar polarization to either pass through or be detected. A filter in the vertical direction will allow vertically polarized photons to pass through, but will block a certain amount of photons with a different polarization angle. A horizontal filter will allow horizontally polarized photons through, but block most vertically polarized photons. The interesting bit comes from using multiple filters in succession. If we put a filter at 45 degrees behind our vertical filter, then of the photons that pass through the first, 50% will pass through the second. The chance to pass through the second filter isn't linear. It obeys square the cosine of the angle difference. So a filter at 22.5 degrees behind a vertical filter will let 85% of the photons that pass through the first to pass through the second. If the second filter is at 90 degrees to the first, then almost none of the photons that pass through the first will pass through the second. But we can then add multiple filters on top of each other to get some interesting results. If the second filter is at 45 degrees to the first, and the third is at 90 degrees, then we might expect that practically no photons will pass through the third filter. Because to pass through the first, the photons had to be vertically polarized, but to pass through the third, they'd have to be horizontally polarized. However, half of the photons that pass through the second filter will pass through the third. We started with vertically polarized photons, but the photons that pass through the second filter act like they are polarized at 45 degrees. And this is exactly what happens. When a photon passes through a filter, it gets polarized along the axis of that filter. So if the particles could pass through the filter at 45 degrees, then the photons are now polarized at 45 degrees. This is sometimes taken to be even more proof of the non-real, non-local properties of particles. Usually this is demonstrated by showing that it's impossible to come up with a clean mathematical expression that can say whether or not a photon that passes through the first filter will pass through the next two. And since this doesn't work, then it is declared that photons must be non-local objects. But it's actually possible to describe this behavior with local and real photons, because photons would have definitive properties moment to moment that they use to interact with the universe around them. So photons that pass through a filter physically and locally interact with it. Through this interaction, the photon either gets blocked, or they pass through, and in doing so get polarized along that filter angle. To create a description of whether a photon will pass through multiple filters merely requires a series of if-then statements. If a photon passes through filter A, then it's polarized along the angle of filter A. This gives the photon X% chance to pass through filter B. If it passes through filter B, then it gets polarized along the angle of filter B. This gives it Y% chance to pass through filter C, and so on. That's all that's required to make a straightforward local and real description of photon behavior. Just like with the original Bell's theorem, every experiment with photons tests a local hypothesis as one where the measured properties of particles are independent of any interaction with experimental setup or the measuring apparatus. They are statistically independent. Such photons gain their properties at entanglement and do not interact with detectors at all. Instead, their properties are just revealed by a measurement being taken. For example, here's a paper on the CH-SH inequality stating as much. This is one of the more commonly used designs and is also part of the collection of works that won the Nobel Prize. The local and real particles described here do not interact with the universe. Their behavior is decided in advance of the experiment, and their properties are merely revealed by observation. Their behavior is entirely probabilistic, and they can't interact locally. But for non-local particles, there's some interaction assumed to take place between photons and measuring device. And it's like this with all such experiments. Photons for a local hypothesis are modeled without being capable of interacting with the experimental setup or measuring device, while photons in a non-local hypothesis do. An alternative local interpretation would just be that photons have some polarization at entanglement, or are polarized during the experiment, after which they travel to a detector and are measured based on the difference between their polarization state and the angle of the detecting filter. This type of local hypothesis, like the one I'm proposing, has not been falsified because physicists don't actually test for them. And so all that these experiments have demonstrated is that particles can't be completely abstract mathematical objects. At least at some point in these experiments, they must have some real properties that they use to interact with their environment, which at the very least looks like it could support a local and real model of the universe. Of course, these experiments aren't just about the correlations in behavior, they're about quantum entanglement. That spooky action at a distance. But I don't think it's any stronger than classical correlations. This was something that became apparent from the quick spreadsheet I created, as the calculations don't rely on the particles being entangled, only that they have opposite spin states during the experiment. There's no need for the particles to have interacted in any way previously. All that the entanglement step does is give the two particles some correlated spin state. But this can be achieved in some polarization step in the experiment. So there's no need for some invisible entangled link between two particles that can transmit information faster than the speed of causality. The only thing needed to explain these results is that the particles have correlated spin states at some time before measurement. There's actually a bit of research being done on very similar ideas, where instead of creating two photons from the same source, two independent sources create two separate and independent photons. These photons are then sent through some experimental design where they only interact with, or become entangled, with another particle at some point before measurement. And these tests still violate Bell's inequality. But it should be possible to push this experimental design even further. It should be possible to have two independent sources create two separate and independent photons, and then have these two particles sent through two independent and separate experimental setups, where they both go through a polarizer before traveling to a measuring device. The way the particles are polarized and how they are measured should be set to match any one of the Bell's inequality experiments currently done. And a pair of photons would then just be two photons that are measured at the same time in these two experiments. The prediction from this interpretation would be that such an experimental design would replicate any result of any Bell's inequality experiment, where what is measured would match the prediction for non-local particles in the original setup, so Bell's inequality would be violated. But if this happens, then it could be interpreted that it's the history and physical properties of the particles that dictate how they are measured, not the act of entanglement or the collapse of the wave function. Because the correlations would come from the polarization step, not from some invisible, instantaneous interaction between two particles that were entangled, which could be caused by the history and physical properties of the particles in a local and real universe. I want to make it clear that I'm not saying that particles can't be entangled, just that it's not stronger than classical correlations, because entanglement has real-world applications, such as quantum computing. A particle with some property goes and interacts with another particle, giving it that property. They are now an entangled pair because their properties are correlated. This other particle can then interact with another particle and give it that property, entangling it with both the first and second particle. This won't continue indefinitely, but it can spread out over some number of interactions. This creates a group of particles with an entangled property. They now form a single unit, or block of information, called a qubit. These qubits are the bits of data that quantum computers use to do calculations or process information, and they are very much real. However, even here, everything can be interpreted through local interactions and classical correlations, because particles must directly and locally interact to become entangled. This entangled state is created from a local interaction that changes the properties of a particle. Even models for how these interactions occur have it spreading outward from local interactions. And from here, there's nothing magical about the correlations of their properties. They interacted, so they share some property. If you measure either one, the measured state will be based off this property. Of course, this entangled state eventually decays. These qubits can only stay active for a brief amount of time, and so can only be used by the computer for a limited number of calculations. In a local universe, this could be interpreted as happening because particles are always interacting with their environment. Just as their properties changed due to interacting with that particle, their properties will continue to change due to time and environmental factors. So entanglement is real, but it may only exist as a physical correlation between the properties of two or more entities. It is not a magical bond between particles that can traverse all of space and time instantly without cause or medium to go through. Okay. To be completely honest, Bell's inequality theorem isn't garbage. While I disagree with the way that the local hypothesis is set up, it's otherwise a fine experiment. The math is sound, and the experiments are cleverly designed. And these results do constrain what is possible in the universe. I just don't think it's in the way that physicists generally claim. Because any theory of the universe should include that particles can't be entirely abstract mathematical objects. They must have properties at some time to interact with the universe around them in some manner. For entangled particles, at least one particle in the pair must have real properties before measurement, and this particle must interact with the measuring device locally and directly. It's also possible that all particles in an entangled group have real properties and interact locally with the measuring device, as this would also violate Bell's inequality. And finally, quantum entanglement is not stronger than classical correlations. If two particles are given correlated spins through some polarization step, then they will have the same measured behavior, statistically speaking, as two particles that have quantum entanglement. This is how these tests constrain theories of the universe. They don't rule out local theories, and can even be used to support them. Because at least at some point, particles must be local and real, otherwise they don't match observations. On the other hand, particles can't be entirely probabilistic and non-local. And that was my case for why local theories haven't been ruled out yet by Bell's inequality experiments. However, even if everything I have just said turns out to be true, this doesn't prove that the universe is local. At best, it can only say that it's still just a possibility. And with that possibility, I'd like to continue to explore a local and real alternative interpretation of physics. In the next video, I will talk about the possible structure and shape of the universe, and why I think the scale of the universe is infinite. Until then, thank you for watching.